Hi, my name is Sam Matlub. Today I'm presenting a topic about how to construct the suffix tree using Ukkonen's algorithm, and this is for class COT 5405 for the fall 2021. Alright, the presentation is actually divided into a few sections. The first section is going to be the introduction, to where we're going to introduce the suffix tree, and we'll talk about the benefits of having a suffix tree. And then we're going to dive into constructing the suffix tree in big O of M cubic algorithm. And so we'll learn about some rules and demo, an example. And then we're going to jump into actually talk about the Ukkonen's algorithm. We'll show some of the tricks that the algorithm is using, and again we're going to do some examples and demo some examples, and at the end of the presentation we're going to summarize everything that we have shown today. So what is a suffix tree? Suffix tree is a special tree data structure that contains all the possible suffixes for a given string or text. Suffix trees can solve many complicated problems in language processing because it contains so many information about the string itself, such as locating substrings, locating matches for a regular expression pattern, finding longest common substring problem, etc. To understand Ukkonen's algorithm easier, we will discuss first how to construct the tree using a naive algorithm, although the time complexity for it is O of M cubed. M is the number of characters in the string. The algorithm, the naive algorithm, involves two loops, face loop, which is an outer loop. We can call it or assign the variable I to it, that traverse each character of the string from 1 to M. And the extension loop, which is an inner loop, which we can assign the variable j to it, that start from the first character and ends at the current character that the face loop is currently processing. There are also three rules that we'll use in this method, which we'll be using in Ukkonen's as well, in Ukkonen's algorithm. The first rule is to add a new character, s of I plus 1, if the path in the tree for the character s of j to I exists. The second rule is to add a new leaf edge or create an internal node if either entire path for the characters does not exist in the tree or the next character in the tree is not s of I plus 1. And the third rule is actually we're going to do nothing if the path is, like the entire path is found and the next character on the tree is s of I plus 1. Alright, so in order to understand everything that we talked about in when I presented the slides and the conversation from the slides about the naive algorithm, in order to construct the suffix tree, I think it's best to go with an example and try to draw the suffix tree or construct the suffix tree using the naive algorithm, and that will actually show the outer loop as well as the inner loop that I mentioned, as well as the rules and how they apply when constructing the suffix tree. And therefore, let's take an example, a string of ax, abx, and let's try to use the naive algorithm to construct the suffix tree. Since we're going to draw the suffix tree from scratch, we always start from the root node. So we always going to have the starting point of the suffix tree as the root node. We also going to always track the outer loop and the inner loop, and therefore we're going to denote and write down where the current index is for the outer loop and the inner loop, and to track them down every iteration. For the first iteration, both the outer loop I and the inner loop J are going to be on the first character A. All right. So therefore, we're going to try to find the path from the root node to the character A. And since we just started drawing and constructing the suffix tree, and it's actually empty, there isn't any path that we can see for the character A that exists right now. And therefore, applying rule number 2, we're going to have to create a leaf edge and label it as A, as so. And that completes the first phase. And therefore, the outer loop will, or the variable I will be incrementing 1 to the next character, which is X. And J will also reset to the first character, which is also A. And now we have to find, and we have to check if currently can find a path to the character A. And actually we do have a path to the character A, and therefore we're going to add the character X to the end of it. And that is applying rule number 1. Then the inner loop will increment as well. And now we're going to try to find a path from the root node to the character X, which doesn't exist currently. And therefore, we're going to draw and create a new leaf edge and label it as X. And that completes the phase, the second phase. And therefore, the next iteration is going to be incrementing I to the next character and resetting J to the original location, which is the first character A. And now we're going to try to find the path for the character AX on the tree, which we can see here. And we'll add the character A that is pointed by the outer loop to the end of the path. And this extension ends. All right, and now we're going to try find the path for the character X, which we can see it does exist. And so we're going to add the character A at the end of it, applying rule number 1. All right, moving J to the next character. Now we're going to check if the tree has a path to the character A from the root node, which it doesn't. Well, actually, sorry, it does. As we can see here. Yeah. So, applying rule number 3, since the character A does exist from the root node, we do nothing. All right, then we increment the outer loop, and so the outer loop and I goes to the next character, and J resets to the initial location, which is the first character, character A. Now we'll try to find the path AXA on the tree, and you can see AXA does exist, and so we're going to add the character B at the end, applying rule number 1. Then move J to the next character, X. Now we're going to try to find XAB on the tree, and XA actually exists, and we can append the character B at the end of the path, applying again rule number 1, and moving J one more time, and now we're looking for AB, in which we can see A from the root node, but we don't see the character B to it. And therefore, in applying rule number 2, we're going to create an internal node to create a leaf edge and label it as B. Right? And therefore, therefore, now we have the path AB as well. All right. Now moving J, another location, and now we need to check if there's a path to the character B from the root node, which I don't think we have, and therefore we're going to have to create a leaf edge from the root node and label it as B. All right, so this phase has completed as well. And now we're going to increment I to, or the outer loop, to the next character X, resetting J to the first character. And now we're gonna check if AXAB exists on the tree. AXAB indeed does exist. So we'll go ahead and add the character X to the end of it. Moving J, one more location. Now we'll look for XAB. XAB does exist. And we're going to add another character at the end of it, X. And this extension ends. We'll move J to the next character. Now we check for AB. And AB does exist. And therefore we're going to add the character X at the end of it, applying rule number 1. And now moving J to the next character, B, and we'll look for the character B, or the path to character B from the root node, which we do have right now, and we'll add the character X at the end of it, again applying rule number 1. And lastly, we will move the index J to the next character, and we'll check if the character X exists, or a path to character X exists from the root node. And as we can see here, it actually exists. And therefore, applying rule number 3, we do nothing. All right. In order to construct a true suffix tree, a true suffix tree always ends with a $sign. So therefore we have to add another character to the string if you wanted to construct a true suffix tree, the $sign character. All right. So let's go ahead and add the $sign to the tree that we're working on to construct a true suffix tree. See how it's going to look like. So since this phase has completed, we're going to increment I to the $sign character, and J will reset its location to the first character and pick A. And therefore, now we're going to have to look for the path for the characters AX, AB, X, see if it exists or not. And if we look at the tree, we do see AX, AB, X here, and we can apply rule number 1 and add the $sign at the end of the path. Moving J one step ahead. Now we're going to look for XABX, which I believe it's in here, XABX. We're going to add a character, the $sign at the end of it. Moving J one location forward. And now we're going to look for a path to the characters ABX. and ABX do exist, and we're going to add the $sign at the end of it, and that extension ends, and we'll move the index or the variable j to the next character b, and we'll do the same thing. dx exists, so we'll add the $sign at the end of it. We'll move j to the character x, and now we check if there is a path to the character x, and we actually do see it here, a path to the character x, but here there's a problem though, because after the character x there is the character a in the path, in the tree. However, we need to insert the $sign instead after the character x, and therefore we're going to have to create an internal node here after the character x and before the character a, and create a leaf edge and label it as a $sign. So now we have the path for x $sign. All right, and we're done with this extension, and j will get incremented again, and now we're going to look for a path to the $sign character from the root node, which doesn't exist. So we're going to go ahead and create a leaf edge for it and label it as the $sign. And that's it. We have constructed a true suffix tree using a naive algorithm, and utilizing the two loops, the outer loop, the face loop, as well as the extension loop, which is the inner loop, as we explained, and also taking advantage of the three rules that we have written on the board. Now the question is, what is the time complexity for this naive algorithm? And the time complexity for it, it should be kind of obvious. It is a big O of m cubic, and the reason, and m as the number of characters for the string. And the reason being is because first we have two loops, the outer loop and the inner loop, which takes a big O of m square. At the same time, when we try to insert or append any character, we keep, as we noticed, as we have seen, we keep traversing each path to the end of it, and compare the characters on the path to the characters that we have in, that we're trying to check. And therefore, the worst case scenario is we will be having m characters on the path, and that will make the time complexity for the whole algorithm, the naive algorithm, to become big O of m cubic. All right, so moving to Ukkonen's algorithm. And the very first thing that I'm going to talk about here is active pointer, which is something that books and articles usually don't start with, but there is a reason for why I wanted to bring this up before anything else. And the reason being is because the things that we're going to talk about later on in the upcoming slides, like rules and tricks, are actually going to use active pointer and active pointer attributes, and they might even change some of these, the values of some of these attributes. So, maybe like understanding the active pointer ahead of time probably make things easier to follow and understand later on when we talk about the rules and the tricks. All right. So what is active pointer? Active pointer is a pointer that helps the algorithm to know and lead it to the location where it needs to start processing. So, for example, if let me get the pen here really quickly. For example, if the algorithm needs to work on the location, If the algorithm needs to work on the location at the character B, right here, in the diagram to the right, so the active pointer using the attributes, the three attributes, is actually going to help the algorithm to know exactly where character B is located at. And that's by setting the active node. And from the diagram to the right, we can see that there are two nodes here in the diagram. So this one, as you may already have figured out, is the root node. So let's give it a label here as an R for root. And there's another node, which is an internal node, right here. Let's give it a label L, for example. So if we're going to work on the character B, this leaf edge actually belongs to node L. So therefore the active node is going to be set to L. Well, on node L we have two edges, one to the right and the other one on the left. And it happens that the character B that we want to have the algorithm work from is the leaf edge to the left of the node. These edges are actually labeled by the position number for the first character on the edge. So for example, X in the string for this tree, the string is AXABX. X is the second character. But if we label the first character as in 0, so A, we'll give it 0, X is 1, A is 2, B is 3, and so forth. That means the active edge, if we set active edge to 1, that actually tells the algorithm that to use the left leaf edge from the node L. All right. On this leaf edge, the one to the left, we have many characters. We have X, we have A, we have B, we have X. So in order for us to tell the algorithm that it needs to work on the character B, we need to specify how far the character B is from the node L. And we can specify, or we can tell the algorithm this by setting the active length to 2. I believe it's 2. Actually, I'm sorry, it's 3. Yep. So if we set active length to 1, that means the location is going to be on the character X. If we set the active length to 2, it's going to reference the second character on the leaf edge, on the edge, and that's going to be A. But if we set the active length to 3, that's going to reference the third character on the leaf edge, and that's going to be character B. So here you go. We were able to tell the algorithm where exactly to start or continue the process from. Remaining is a variable that tells the algorithm how many suffixes still needs to be created in order to complete the construction for a true suffix tree. And that will be explained more when we start, when we take an example and show how to construct the suffix tree using the Ukkonen's algorithm. On the other hand, the end variable specifies the position of the last character that's been processed by the algorithm in the string. So for example, if the last character that being processed is the character X, then since the position of character A is 0, or the position starts at position 0, then X is going to have the position number 1, and therefore end going to be equal 1. If the last character that we processed is the character B, then end is going to have the value of 0, 1, 2, 3. So end is going to set to 3. And in this example, with string AXABX, if we finished processing all the characters, then at the end variable gonna get set to 0, 1, 2, 3, 4. So it's gonna be set to number 4. Okay, now we're gonna talk about the tricks Ukkonen's algorithm follow to make the algorithm faster. First trick is the skip count edge label compression. And the idea behind this trick is that instead of matching path character one by one on the edge, we can check if the number of characters on the edge is less than the number of characters that we need to travel. And if so, we can jump right to the next node instead. And otherwise, we would skip to the last character on that edge. Also, when labeling the edge, it was found that it is easier to label it with a range of characters or range of characters positions with respect to the string under analysis. And therefore we'll see label like, as shown in the diagram below, 3, 4, which means that the edge has the characters that has a position of 3 through 4 on the string, and so forth. The second trick is whenever we encounter rule 3, referencing the rules from the naive algorithm that we discussed in the previous slides, we stop the extension loop or exit out of it, and we move to the next phase loop instead. And the third trick talks about removing the end range number from the first trick that we just talked about, and replace it with a global variable, end variable, which we talked about in the last slide. And that variable, that end variable, will get updated in every phase. Another concept that Ukkonen's algorithm uses is what is called suffix links. And what a suffix links is a link that connects two nodes together in a way that makes the algorithm to move from one location to another location really fast. However, in order to link two nodes, there is a certain condition that has to exist before the algorithm can connect two nodes together in a suffix links. And that is for an internal node that is recently created, and let's call it V, for example, with a path XA, where X is a single character and A is a possibly empty substring. If there is another node on the tree with path A, then this node, the latter one, is a suffix link to the first node. We find suffix links during extension loops, and they help travel, as I mentioned, and jump from one location to another where the algorithm needs to continue processing and constructing the tree. During any extension loop, the first internal node created during that loop will have a suffix link to the root node. If on that extension loop we had to create another internal loop, then the destination of suffix link for the first node will move to the newly created node. All right, few more extra rules and we should be good to go to start constructing suffix trees for any string using Ukkonen's algorithm. So every time we apply rule number 2 and create a leaf edge, we need to remember to decrement the remaining variable. Also, during any extension loop, if the active length is set to 0, we need to check for the path to the character from the root node. And if it doesn't exist, then we need to apply rule number 2 to create the leaf edge and create a path from the root node to that character. Also, if we encounter rule number 3, which is the showstopper, we need to remember to set the active edge and active length to the current path and the current character location where we encountered that rule. When applying rule number 2, we need to check if active node variable is set to the root node. And if so, we need to remember to increment active edge and decrement active length. And if the active node variable is not set to the root node, we need to follow the suffix link and continue working on the suffix tree. And right now I think we have all the information we need about the Ukkonen's algorithm to start working on strings and start constructing the suffix trees for any string. Alright, so what I'm going to do this time is I'm going to take the same example that I solved and constructed the suffix tree with, and I'm going to try to use the Ukkonen's algorithm to construct the suffix tree for that example. And so therefore I got the string in here, AXABX $, and I got my variables to the side of it. The remaining variable, which is right now set to 0, active node set to the root node, active edge set to -1, active length 0, and end is set to 0, which means I'm actually going to process the very first character. Well, first thing first, we need to get the root node and the suffix tree. And now, since we are processing the character A, the remaining is going to be incremented to 1. And I believe everything else is going to stay the same. So the active root is the active node is root. The active edge is going to stay the same. The active length is going to stay the same. And all right. So now we need to find and check if there is a path from the root node to the character A, which obviously we don't have, and therefore we're going to create a leaf edge and label it as an A. Matter of fact, this label is only for us. As indicated in the slides and previously, is with Ukkonen's algorithm, we're going to use a range of the string or character positions in the string, and therefore the label should be something like 0, comma, and end. And end is actually referencing the end variable here. Alright, so since we applied the rule number 2 and we created the leaf edge, the remaining got decremented to 0. And now we're ready to move to the next character, which is X. Okay, and since now we're processing the second character, the remaining is going to be 1. And the end is going to increment to 1 as well. And we look on the the tree, on the current tree, and we append x on every leaf edge to the end of the path. And so therefore we're going to add x right here. Rule number 1, if we remember from the naive algorithm. Alright, so active length is still 0, so we still need to check if the character x has a path in the tree. And as we can see, there isn't any path from the root node to the character x. And therefore, we're going to have to create this path by creating a leaf edge, applying rule number 2. And this will be labeled as 1 end. And since we applied rule number 2 and created a leaf edge, then the remaining is going to be decremented, and now we have a 0 for the remaining. Alright, so now we are ready to go to the next character A, and therefore the remaining is going to be incremented to 1, and the end variable is going to set to 2. And we're also going to append and add the character A at all the leaf edge or leaf edges on the current tree. And therefore, we're going to add A in here, and we're going to add A in here. So we have AXA, we have XA. Active length is still 0, so we're going to have to check if there is a path from the root node to the character A, if that path exists. And if we look around, we actually see there is a path to the character A from the root node, and that's right here. So let me just put it a little closer here. Here we go. And because we found a path to the character A, then that's actually a rule number 3. We do nothing, but it's a showstopper though with Ukkonen's algorithm, and therefore what we're going to do, we're going to update the active edge and active length, and I forgot to update the end variable. Active edge is going to be 0 in this instance, and active length is going to be 1. And because we hit rule number 3 right here and a showstopper, we're not going to decrement the remaining. So the remaining is going to still 1. Alright, and we move forward with processing the next character. So we're moving from A to B. And because we're moving to B, we're going to increment remaining. So the remaining was 1, so now it's going to be 2. The end variable is going to be incremented to 4, 0, 1, 2, 3, 4, the position for the character B. And then we're going to add the character B to all the paths on all the edges in the current tree. So we'll add B right here, and we'll add B right here. Alright, and now we're going to check if there is a path from the character A to character B. And there isn't, because the character next to A or after A on this edge is X. And therefore, we're going to apply rule number 2 and create an internal node right here, and create a path for the character B. And that's going to be 4 and because we applied rule number 2, we're going to decrement remaining to by 1. So that's going to be 1. right? And let's update this. So this label is going to be 0 by 0, and this label is going to be 1 by end. And because we applied rule number 2, we're going to decrement active length, and we're going to also increment the active edge. So this is going to be 0, and this is going to be 1. And because active length is 0 now, we have to check if there is a path from the root node to the character B. So if we look around, we don't see any path to the character B, and therefore we're going to apply again rule number 2 and create an edge with a label B, again from the root node. And this is going to be 4 by end. Alright? And because we applied rule number 2, we decrement the remaining to 0, or decrement it by 1, so the remaining now is 0. And I think that's it for this iteration. So we're ready to go further to the next character. So we move to the next character, which is x, and the remaining therefore going to be incremented to 1. And the end variable going to be incremented to 1 as well. Alright. So I think we're ready to process the character x. So we're going to add x to all the paths on all the edges we have on the tree. So we will put x in here, put x in here, add x in here, and add x in here. And because active length is 0, we're going to ask or check the current tree if there is a path from the root node to x. And we actually have a path to from the root node to the character x right here. So let me get the character x a little closer. Okay, so that going to be a showstopper, rule number 3. And therefore, we're going to keep the remaining as 1. We're going to update the active length and the active edge accordingly. So the active length is going to be 1, and the active edge is going to be 1 as well. Now we move to the next character. The remaining is going to be 2, set to 2. The end is going to be incremented to 5. Alright, let's see what we have right now. We add $sign on all the edges, on all the paths. Alright, and now we check if the character right after X is a $sign, and it is not. The character after X is A, therefore we apply rule number 2. We create an internal node right here, and that's going to be the $sign, and that's actually going to be 5 end. And this will be corrected. This is going to be 1 by 1. This is going to be ABX. So 0, 1, 2, 2 by end. And because we applied rule number 2 in here, we are going to decrement the remaining. And because we're still on the root node and the active length is not 0, we're going to go ahead and decrement active length and increment active edge. But because active length is 0, now we have to check if there is a path from the root node to the $sign. And I don't think we have a path from the root node to the $sign. And therefore, we're going to go ahead and create one. Apply rule number 2 again. And that's going to be 0, 1, 2, 3, 4, 5. All right. And because we applied rule number 2, the remaining is going to be decremented by 1. So we have remaining right now to 0. And I think that concludes the construction to the suffix tree. So let's go ahead and compare what we have constructed right here using the Ukkonen's algorithm versus the naive algorithm. So we have the root node. From the root node we have an edge or a path to the $sign, just like here. And we have another path to BX $sign, which we have right here, BX $sign. And we have an edge or a path to X, and then from X it goes to the $sign, so X $sign. And if we continue from X to the other edge, then we have X ABX $sign, X ABX $sign. And on the other side, on the left side to the root node, we have A, and from A goes to BX $sign, and we have BX $sign as well. And if we continue to the other edge, we have X ABX $sign and AXA BX $sign. So the suffix tree that we constructed using the Ukkonen's algorithm is exactly the same as the one that we created using the naive algorithm. So we actually have a true suffix tree, but this time using Ukkonen's algorithm. And as we have noticed, we haven't really done that much traversing on the strings, rather than we went like character by character, and we traversed only all the characters on the string. Versus in the naive algorithm, we were like we traversed multiple times. So we had 2 loops to traverse all the possibilities for the suffixes in that string. And therefore, the time complexity for the Ukkonen's algorithm is actually big O of m, versus the naive algorithm, as I mentioned, and because of all the loops, as well as the time the algorithm takes to traverse to the end of the characters in the path, in any path at any given edge, and therefore the naive algorithm took a big O of m cubed. One thing that I forgot to mention while I was constructing the suffix tree using the Ukkonen's algorithm is actually every time that I applied rule number 2, I forgot to show the suffix link. And it just happened that in this example, we didn't have to traverse to a different nodes using the suffix links, but for what it's worth, every time that we applied rule number 2, like I said, and created a leaf edge, there should be a suffix link from the internal node to the root node. And because we haven't really created two edges or two internal nodes, in the same, on the same extension. So basically all the leaf edges that we created in this example are actually going to be referencing the root node as a suffix links. To summarize, at first I talked about a naive algorithm to construct a suffix tree that takes big O of m cubed. Then I talked about Ukkonen's algorithm to construct the suffix tree and techniques used to improve the naive algorithm that made this algorithm to only take big O of m of time complexity. Finally, here is the references I used for the topic that was covered in this presentation. Thank you very much for watching and feel free to reach out for any questions.